machine learning, or if you've built machine learning models using Python, this is probably going to be a bit trivial, but if you've not done it before, this is going to be very, very helpful. Okay. What I have in mind for today is the following. I'm going to wrap up the lecture from yesterday. So we'll talk a little bit about deep neural networks. As I mentioned earlier, somebody else is going to delve deeper into deep neural networks later this week. I'll wrap up what I started yesterday, and then I will spend this morning some time on data pre-processing, a little bit on data visualization. I'll also give you some examples of clustering, classification. And in the afternoon, or perhaps in the morning itself, in the second session, we will focus on clustering and classification. Okay, so that's the idea. Any questions? Okay, all right, let's get going. So I went through this slide yesterday, not going to repeat it, just I have it here to refresh your memory, because we went through these slides as well, artificial neural networks. Okay, so I think we paused somewhere here when I introduced many-to-many recurrent neural networks. Okay. Now somebody asked me yesterday, how is it that deep neural networks are learning the representations? Yesterday I talked about how representing your data or transforming your data into the right form would help you in building better models, right? So what is it how is it that deep neural networks are automatically finding these underlying transformations or representations of data? I mean, we don't fully understand how this works, but it's roughly explained in this fashion. Now you have what you have here is some sort of a neural network, perhaps a convolutional neural network, and the goal of this neural network is to take images and identify them as those with cars, persons, or animals. Okay, so that's the classification problem. And each of the layers in the neural network has a certain role to play. For instance, in this neural network, the first layer identifies the visible layer from the image. The second layer, or the first hidden layer, it identifies the edges of this image. The third layer, corners and contours, and then the fourth layer, different parts of the object, eventually letting you know whether the image is a car or a person or an animal. That's the way to think about or understanding or interpreting these neural networks. They're very complex. There's a lot of stuff happening inside, and each of these layers are playing a role in identifying certain features in the input. In this case, these are images, so these layers are trying to identify different features of these images. Did I show you this figure yesterday? No, right, okay. I think while talking to some of you during the break, I mentioned something called universal approximation theorem. Right? Neural networks approximate some underlying function that you're trying to, that generated your data. Right? So when you have data from a system, there is most likely, you can assume that there is an underlying unknown mathematical function that is generating this data. And with neural networks, what you're doing, or with other models, what you're doing is approximating that underlying function using whatever algorithm or the method that you have. With neural networks, you're using these neurons, the activation functions, to approximate an underlying function. And there's something called universal approximation theorem, and it says that it's possible to approximate any continuous function in a compact set using a single layer with finite number of neurons. Okay, so if you use a finite number of neurons, but many of them, you can approximate almost any function using a neural network. That's a good reason for building neural network models. Right? So if you have enough neurons, in your neural network, then you can approximate any function. So no matter how you're generating data, where you're getting the data from, if you have a large enough neural network, you can approximate it. That's what the universal approximation theorem says. And this graph here is something that I took from Andrew Ng's course. It shows the amount of data that is available on the x-axis and the performance of various machine learning algorithms on the y-axis. Now, this is not, this is just for illustrative purposes. It's not theoretically correct, or it's not based on quantitative measurements from these algorithms. It's just a rough idea, right? It's also something that you'll find in Andrew Ng's course online. If you look at, if you focus on the left-hand side, this corner here, what you'll notice is that when you don't have enough data, when you have limited amount of data, the performance of various machine learning algorithms is more or less the same. Okay, so it may vary or depend on the type of problem you have, the type of nonlinearities in your problem, the type of data, the amount of noise, etc. But it's very difficult to differentiate the performance of support vector machines from logistic regression or other learning algorithms, okay, including neural networks. They all seem to perform more or less the same way when you have limited amount of data, not a lot of data. But on the other hand, as you increase the amount of data that you have, these classical machine learning tools or algorithms, their performance appears to taper off. Meaning, if you have, let's say, a logistic regression model, the performance of the model is not going to improve if you add more data to the problem. Okay, so you can add as much data as you want, but the performance is not likely to improve. And it makes sense, right? So when you have a model with limited structural flexibility, a logistic model has limited structural flexibility, and therefore, even if you add more data, you're not going to get better performance. Okay. On the other hand, if you have a deep neural network, let's say with 10 layers, you will find that as you increase the amount of data that is provided to this algorithm, the performance of the model keeps getting better and better. And if you increase the number of layers, you're likely to get an even better performance. Okay, so that's why neural networks are, deep neural networks are so popular, because when you have, especially when you're operating in this region where there is a significant amount of data, you're likely to get much, much better performance with neural network. On the other hand, when you don't have enough data, when you have limited amount of data, then any of these methods would likely give you the same performance or similar performance. Yeah, it may not perform well, yeah, because neural networks have lots of parameters, and when you don't have enough data, they may not give you as good a performance as other methods with limited, with more, with less structural flexibility or fewer parameters. And in fact, there's a paper that we published where we try to compare on an industrial problem deep neural networks with logistic regression and a few other methods for classification. We had a lot of data. We had gigabytes of data, and yet we found that logistic regression outperformed deep neural networks every time. Right? But there's no theoretical way of confirming beforehand which method is going to perform better. Right? There is an element of trial and error involved here. So when you start modeling, you may want to start with the simplest model possible and then slowly increase the complexity until you're satisfied with the performance of your model.
Hello, sir. So could we make a comment on the data itself? Whether it doesn't matter which algorithm you use, if data is not refined or means certain data will not support some algorithm. Can we make such assumption or not? Means let us say if there's some data, if it doesn't matter, if you put a deep neural network, it will not give a good performance, whereas that data, if you use some support vector machine
right.
regressions, it will give a better performance.
Right. I guess the question is, can you a priori tell that some methods are not suitable for a certain problem? So you can sort of narrow down the methods you're going to explore on a given problem, right? I think the distinction between linear and nonlinear methods is perhaps easy to make. If you know that your data are nonlinear, then you don't want to use linear regression on that, right? So that's a simple thing to do. But beyond that, sometimes, in some, so for instance, I work with a colleague on growing what are called CHO cells. These are Chinese hamster ovarian cells. Those are used in making recombinant proteins. They're used in drugs and so on. The process is very interesting. It has an initial lag phase. This is, we measure the number of cells that are made per unit volume in that process. So you initially the cells don't grow, so you have the lag phase, and then there's an exponential phase, and then there is a stable phase. Okay, so it sort of looks like this, the output of that process. Now this looks very much like a logistic curve, so it made natural sense for us to use logistic models for this data, right? So sometimes in the data, you might find patterns that are similar to the functions that you're using in these machine learning algorithms, right? So, and if that is the case, then you may want to use that intuition, prior knowledge, to pick the right functions. Yeah. Right. Yeah, that's a very good question. I think a lot of people have tried to figure out what's if I have a budget of neurons. Say I'm only allowed to use 100 neurons. What's the optimal configuration of these neurons to get the best performance? I believe there are some papers on it, but I'm not fully familiar with that work. The more common thing to see in literature is people trying to do this through trial and error. Right? I think that there are some pieces of research in that area, but nothing that I'm familiar with that's become popular for everybody to use. If there is something that is very reliable, it's quite likely that the neural network algorithms that are in Python are already implementing that. People have also noticed that when you use a lot of neurons, there's a bit of, how do I put this? A bit of randomness. There are probably multiple solutions to your parameter estimates that give you the same output, right? So there's going to be a bit of redundancy in the model. But sorry, I don't have a good answer to that other than to say you have to try and see different. Now, I talked about transformations or representation of data yesterday, and the performance of machine learning algorithms is known to depend heavily on the representation of the data, right? So if you represent your data, for instance, you may want to use a logarithmic transformation on your temperature measurements. And sometimes when you do that, especially in reactions or reactors, you might get much better performance, right? But finding those representations is not easy. How do we know? If you have a reactor and you have some intuition into the science behind it, then you might be able to figure out what that representation of that data is going to be, right? So let's try to visualize this, and then. So if you have some, say, temperature that you're measuring, instead of using temperature, say you use logarithm of temperature, and then build a model. That's likely to be better than try trying to do this. Not always. I mean, this is our representation. Okay, I have a much better example coming up in the next slide, but this is a representation of your data. Your data are features. So you have a feature, and there's some representation through trial and error or experience or some intuition into the problem. You figured that this representation is better for the models that you're trying to build, the structures that you're employing to build this model, right? So this is better. You can also do this, but you're not likely to get the performance that you're getting with this. And this transformation is what is called representation, new representation of the data. And each piece of information included in the representation of the problem is known as feature, which is exactly what I wrote here. And many artificial intelligence problems can be solved by designing the right set of features and then feeding them into a machine learning algorithm. Okay? By designing the right representations. If we get the right representations, you're likely to get much better performance. So here's an example that highlights this point. So on the left-hand side, you have a classification problem where there are 3 different data sets. If you want to classify these data sets, you will have to come up with these straight lines that separate these different data sets. Okay. Now in that case, visually it's very obvious what those lines. I mean, it's not very obvious, but there are many different ways in which you can separate these 2 data sets. You can draw a line like this, or you can draw a line like this. They will all separate those data points. There are ways in which you can find a unique separating line. We'll come to that in a later lecture. But the point I'm trying to make is when you have data like that, finding these classification boundaries is not very hard. You can just draw a straight line, right? On the other hand, if you look at the data on the right-hand side, I have light blue triangles and dark blue circles in the center. Now, I can't think of any straight line that is going to separate these 2 data sets, right? It's not possible. However, if I can take this data, these data are in Cartesian coordinates, okay? And transform them to polar coordinates, use r and theta as my x and y axis, then that data would appear in this form. Right? So why is that the case? This is essentially a circle. The r, the radius of all of those points, is in a very narrow band, right? Which is what you see here, and this is the corresponding polar angle. The same is true with this other data set. Now, after transformation, it's very easy to separate these 2 data sets. You can just draw a straight line, and you can find that classification boundary. Right? So that's the power of transformation. In this example, you are transforming your x and y's in Cartesian coordinates into polar coordinates. Once you do the transformation, separation of these 2 data sets is extremely easy. Sorry about that. All right. The last topic, which I'm going to cover in greater detail on Friday, is deep reinforcement learning. How many of you have heard of reinforcement learning? I probably mentioned it once or twice. You've heard, okay. What is deep reinforcement learning? I mean, reinforcement learning has been around for a long time. It's based on a mathematical optimization problem. Roughly speaking, the idea is as follows. By the way, one of the scientists who has worked in this area for 3 or 4 decades is Rick Sutton. He has a very nice textbook on reinforcement learning. If you get an opportunity, read that textbook. He received the Turing Award 3 or 4 weeks ago. Turing Award is considered the Nobel Prize in computer science. Roughly speaking, this is how it works. You have some environment, a system, an external process that you want to control. You want to, the behavior of which you want to manage, right? So that's your environment. And the idea behind reinforcement learning is to design an agent or an RL, reinforcement learning algorithm, that sends probing signals to the environment, okay, generates a response, uses that response to update itself, and continue through this loop, action, exploration, and exploitation loop until it's able to achieve an objective that you give the agent. So when you start this process, you give the agent an objective, something that it's supposed to achieve. I'm sure all of you are familiar with control. In undergrad, electrical engineers, you know control. In control, your objective is to track set points, right? Now, that can be an objective that you provide your RL algorithm. The RL algorithm then probes the environment, generates the data, understands its behavior, and figures out a way to take actions so that you are always tracking the set point. Okay. So that's roughly reinforcement learning. It's used in a wide range of areas, very widely used in gaming. It's also used in fine-tuning large language models. They use something called reinforcement learning with human feedback. The idea there is you give your large language model a certain input. It provides an output. Then you have a human looking at the output and deciding whether it's good or bad. This process is embedded in a reinforcement learning framework. Okay. This picture shows what I mentioned earlier. You have exploration. You put up the process and learn its dynamic behavior. Once you generate the data, you use it to learn to use it to get your process to behave in the way you want it to. There's a very popular approach called actor critique approach, where an actor finds an optimal policy and the critique evaluates the current policy and decides if the actor needs to be updated. Okay, so this is at a very high level, so don't worry if you don't fully understand what's happening here. We'll get back to it later. That's the standard reinforcement learning, and in deep reinforcement learning, the idea is to approximate the actor and the critique using a deep neural network. All right. I just wanted to tell you a little bit about the work that I do in my research group, and then we'll jump into data pre-processing. Oops, sorry. At a very high level, the goal of our research group is to build these self-driving industrial processes with cloud onboard AI-enabled intelligence, self-diagnosing, self-maintaining assets, virtual assistants, virtual reality-enabled control rooms, all of this while making sure you're able to achieve optimal performance while maintaining safety and high standards of safety and reliability. That's our goal. That's what we are trying to build. But in order to get there, there are different pieces to the puzzle that we have to put together. We work with a variety of natural resource industries. Canada is a natural resource intensive country, or it has a very large natural resource industry, so we work with them. quite a bit. For instance, what you see on the left-hand side is a paper machine in that video. Have you ever seen paper machines? Paper making is almost 2,000 years old. It was invented in China, I believe. It's not very difficult, but you can make that paper machine. It's the end of a paper machine. They make paper at speeds of 120 kilometers per hour. That's how fast it's made, and you roll it into that into your big roll at the end of the paper machine. So we work with different bio products or forest products industries. We work with a variety of mining industries, oil and gas industries, biotechnology, and pharmaceutical industries. Right. So these are some of the industries that we work with in my research group. We also work on smart buildings, space and energy management, advanced battery management systems. I know some of you here are interested in battery management systems. More recently, we're looking at material discovery using AI tools. The idea there is to develop new materials for carbon capture and conversion. We also work on health analytics. This is a project with a communications company in Canada called Rogers, where we are collecting data from patients in emergency departments, putting it in the cloud, and processing it so that the patients are triaged much more efficiently, and they don't have to stay in emergency departments for too long. The average time that patients spend in emergency departments is about 7 or 8 hours. We're trying to bring that down through efficient monitoring of patients using AI tools. Now, you're probably wondering what's the common thread connecting all of these different areas. In all of these different areas, we generate a lot of data. The data often tend to be heterogeneous, meaning there are time series data, categorical data, images, videos, text, etc. The data are noisy, they're stochastic, they're often very nonlinear as well, right? So, but the underlying systems, the dynamics, they're all very similar. So we take that data and use it to solve 4 different problems primarily. We do data visualization. I am a firm believer in visualizing the data first before you apply any machine learning tools. And in fact, I think you can get a lot of information out of your data by simply visualizing it. Visualize your data first before you do anything else. And that itself can provide significant amount of prior information before you start building machine learning models. We're also interested in building digital twins or these large-scale models using different machine learning tools. We do post-mortem analysis on data called predictive analytics. This is we actually published this data as a benchmark problem. This is an electric furnace in a copper mine. This furnace has, these furnaces are really large, by the way. They're probably bigger than this room, or as big as this building. The furnace melts copper ore, and before it's purified. And because it's an electric furnace, it has 2 electrodes in it. There is an electric arc that forms at the bottom of the electrode on the surface of the molten ore. In this particular example, this is, as I said, this is released as a benchmark problem. You can go to my website and download this data set and try it for yourself. So the problem is these electrodes, every once in a while, they lose the arc at the bottom of the electrode. Okay, so when you lose the arc, you're basically breaking the circuit, and the furnace shuts down. We don't know, nobody knows why that happens, but my hypothesis is the resistance of the ore changes depending on where it's coming from and what impurities are in the ore, right? And we don't know when that resistance changes, and when that resistance changes, the electrodes lose the arc at the bottom. Okay, and when they lose the arc, you break the circuit. The furnace has to be shut down and restarted. That's a lot of effort, and typically every such incident, this company loses about 15 to 20 minutes. It takes 15 to 20 minutes to restart, and they see 800 to 900 events of this type in a year. Okay, so that translates to 2 to 3 weeks of lost production time. That's a lot of time to lose in a year, right? So they wanted to, when this company came to us, they wanted us to build a model using historical data that can predict with 75% probability an arc loss 5 minutes in advance. Okay. So we built different types of models, including linear models, linear classification models. We built logistic regression models. We built convolutional neural networks. We built all sorts of models. But in the end, it turns out that none of these models actually outperformed a simple logistic regression model. So what kind of data? There are about 110 different measurements on that furnace. It's a massive furnace, and it has 110 different measurements. About, I think, 99 of those measurements are time series measurements. 10 or 11 are categorical measurements, meaning a valve is open or closed, that type of data. When we started working on this problem in 2018, when everybody was trying to figure out how to use deep learning models in the context of industrial processes. When we received the data, my students, 2 PhD students, worked on it for nearly 6 months to pre-process the data, to remove all the unknown features in the data before they started building these models. At that time, they were not even able to open the Excel spreadsheets in which we received the data because they were just so massive. The data was collected over a period of 2 years. All of this data, by the way, is available on my website. If you go, or if you send me an email, I'll send you a link. We have proposed this as a benchmark problem in machine learning, in fault detection at that time. This is an interesting spiral plot that my student came up with. It shows the entire workflow, right? So you have the process, it generated data, the Excel spreadsheets, then they did different types of transformations, they did visualization, they plotted histograms, et cetera, eventually building different types of models. So we do predictive analytics. We also do post-mortem analysis on historical data. Once you collect data, you can look through it and understand what has gone wrong the previous time. Now we also build models for predictive analytics, meaning we want to have models that predict when something might go wrong, right, in advance, so that we can take preventive action. So in this case, for instance, if the operators know that they're going to lose the electric arc 5 minutes in advance, all they have to do to prevent it with high probability is to lower those electrodes. If they lower the electrodes a little bit, they're unlikely to lose the arc. And that saves them production time. All right. So those are 3 main classes of problems that I work on. And the last class of problems are around optimization and control. They're so here we want to take optimal decisions under uncertainty. You don't have all the information. There's a lot of noise in your data. Things that you don't know, you want to be able to take decisions under those circumstances. And for that, we have used reinforcement learning mostly. There's a lot of work we've done in the last 6-7 years on reinforcement learning. These pictures here show, this one here shows the state of the art, meaning you have a process, there's a controller, PID or MPC or whatever, and then there are people who are trying to maintain these controllers. Okay. This was work done by Honeywell. So we went to Honeywell and we said, we can replace your controllers with reinforcement learning agents and deep neural networks. And then they said, they already invested a lot in existing infrastructure and software, hardware. They did not want to make dramatic, big changes to the existing infrastructure. So we came up with this intermediate solution where we are, instead of replacing the existing controllers with reinforcement learning agents, we design reinforcement learning agents that maintain existing controllers, okay, or fine-tune existing controllers. What you see here is a pilot scale plant at Honeywell location in Vancouver that we used to design a reinforcement learning agent. Yeah. Yeah. Right. There is a software aspect. So Honeywell built a piece of software for us to interact with this system, which is what we used. Hardware, of course, they provided all the hardware. It was existing. We just used our algorithms to fine-tune the hardware that's already there. Now, in this case, the controller was a PID controller. We designed a reinforcement learning agent on top of it, and the agent was adjusting the controller parameters, gain, time constants, the proportional gain, integral time constant, and the derivative time constant. So it was tuning those parameters. The existing infrastructure, the PID loops, etc., they are exactly the same as what they had before. The only difference is you now have this controller or agent that's overseeing the performance of PID controllers. No. We just had to figure out a way to communicate with the controller using software. So in reinforcement learning, there are different ways in which you can do that. You can do reinforcement learning with no model at all. Okay? So you don't have a model. Your reinforcement learning agent is just probing the system, generating the data, and developing, these are called policies, which are essentially control algorithms. So if you think of a PID loop, right? Are you an electrical engineer? Do you know? Okay, so you know the basics of control. So when you want to design a PID loop, you build a model, and then there are some standard tuning methods you can use to extract the controller parameters, right? But the model itself is not explicitly in the PID loop. There are certain versions, IMC, for instance, internal model control. You can embed the model explicitly. But the PID controller itself, there's no explicit model, right? So you can think of reinforcement learning in a similar way. There is no explicit model in it. You're just, the agent has certain parameters, you're fixing those, and that's pretty much it. You're not explicitly building a model. But there are different variants of reinforcement learning. One where if you have a good model, you can give it to the reinforcement learning algorithm, and it will use it to provide you better performance. If you provide it with a model, then it doesn't have to probe your system all that much because it has the knowledge already. Right? From a data perspective, it's a lot more efficient if you provide it a model. Now, there are two. When we started this work, we very quickly realized there are two big problems. One is reinforcement learning algorithms are data hungry, meaning if you don't provide it a model, then it will probe your system quite a bit before it starts controlling it well, right? Which makes sense. If you don't give it any information about the model, then it has to probe the system. When it starts probing the system, it generates a lot of data, or in other words, it takes up a lot of time and valuable process operational time, right? So every time when you're using these tools in real time, you have to probe your real system. And when you probe your real system, you're likely making off-spec product, which you cannot sell, and therefore that costs you money, right? So typically in the industries, they don't like systems that probe the process quite a bit. That's not preferred. So that's turned out to be a big problem with this reinforcement learning algorithm. For instance, one of my students compared reinforcement learning with off-the-shelf Honeywell auto-tuners. And he found that a Honeywell auto-tuner would tune a controller in about 5 minutes. Reinforcement learning takes about 50 minutes, right? It's almost 10 times more time. That's because we did not give it any model, whereas Honeywell auto-tuners, they do a couple of step changes, come up with the data, build a model, use that for tuning the controller, right? So they were much faster. So we found that that's a big problem with reinforcement learning algorithms. They're data hungry. And number two, as these systems are probing the system, probing the environment, and generating data, before they actually reach an optimal policy, they still have to be stable in closed loop. You don't want your algorithm to operate in such a way that before it reaches the final optimal solution, it becomes unstable, and that's not going to be helpful, right? So we found that there are two big problems. Stability is one, and the other one is the fact that these algorithms are very data hungry. All right. I'm just going to wrap this section up with a few examples. So this is the setup that I talked about, the Honeywell setup. That's Nathan Lawrence, my student who did this work. What you see on the left-hand side is the interface that was developed for us to interact with Honeywell hardware. Okay, this is another student, Shuyan Wang. He also worked on reinforcement learning. In this example, he's trying to land a rocket on a launch pad. This is clearly a simulation. But the difference between his work and Nathan's work is that Nathan assumed that he did not have a model. And then when we realized that reinforcement learning is very data hungry when you don't provide it a model, we asked Shuyan to come up with ideas for modifying the reinforcement learning algorithm for problems where we have some partial information about the model, right? It's very rare that you have no model. You often have partial information about your model, about your process. So we asked him to figure out how to incorporate partial information into reinforcement learning in order to improve the data efficiency of those algorithms. So he came up with a couple of ideas. Some of those are already published. If you go to my website, you'll find those papers, Shuyan Wang's papers. This is also an example by Shuyan where he's trying to track, get his robot to track a certain path. Again, we have only provided partial information to the reinforcement learning algorithm. Ibrahim Youssef is another PhD student. He's going to be graduating in a month. He worked on what I would call visual analytics. We are probably one of the first to do this type of work. Very early in 2018 or 2019, I realized that much of the success in artificial intelligence is because of the algorithms they developed for image classification, video processing, etc., with the convolutional neural networks. So there's something unique about those convolutional neural networks that's giving them such high performance. So I asked Ibrahim to see if he can use those image processing algorithms on time series data and achieve similar performance. Right? He did exactly that. He took the process data, time series data, represented it visually as an image, and then applied image-based approaches for prediction and decision making. Okay, so this is a pretty cool piece of work. Check out his papers on my website. And that is Shuyan Wang, Jingyi Wang. She did her thesis. She just finished it a month ago on digital twins for individual units as well as large-scale plants. She came up with. What is this? Okay, yeah, that's a great question. Now, you all know what a model is, right? So if you have an individual process, you can build a model, say a dynamic model, right? A digital twin is in some ways like a model, okay, but has other additional features. If you build a model, typically you're not adapting it online. You build a model once and it sits there. With a digital twin, there is this two-way interaction between the real system and the digital twin. The digital twin is supposed to represent every aspect of the real process exactly. Okay, so it's a true replica of your original process or network of processes. So in this case, for instance, we have all these different processes. They are interconnected. Are there any chemical engineers here? You're chemical engineers. Have you used any simulators, Aspen simulators, HISYS, etc.? Those are mostly static simulators, meaning that you use static models. You can also use dynamic models, right? So you can think of digital twins as those simulators, but a bit more sophisticated, and they should represent the real process exactly, right? Let's say, let me add the caveat, to the extent possible. You're trying to replicate exactly what happens in a system, in a process, in a plant, in simulations. Okay. Typically, when you build models, that's not what you're looking for. So you build a model for control. You take just one unit and one combination, perhaps, of variables, and you build a model between those two, and that's it, and you use that model, right? And those models don't necessarily replicate the entire behavior of this system exactly. For control and other purposes, you don't need to have a precise model. You can still do away with an imperfect model. You can achieve good performance. The idea behind digital twins is to incorporate every aspect of this system into one model. That includes the dynamic models and sensors and all this stuff and all the measurements. There are many companies right now that are providing this as a solution, digital twins. They can build a digital twin of many industrial processes. Has anyone here tried those digital twins? Or have you taken a demo of those digital twins? They create a simulation of your entire plant. So you can actually walk around in simulation. Sometimes, some of them also have these virtual reality goggles. So you put them on, you can, in software through those virtual reality goggles, you can just walk around your plant, you can see all of the different instruments, the sensors, their readings, etc. Right? So that's a digital twin. And with the digital twins, you can also you can make changes to your process and see how your process responds. Right? So you can do. So for instance, say I want to remove a pipe here and add something else, or I want to add a different valve, I want to add a different sensor. I will be able to do that with a digital twin. But if you have a model, those are things that you cannot account for. Right? There are jokes about digital twins being just models, right? There are people who would say, yeah, digital twins are essentially models with a new name, right? To some extent, that's probably true. But the way digital twins are, the phrase digital twins is being used, there's this subtle difference. That's the way I interpret it. A digital twin is an exact replica of your true process, whereas models are not necessarily the exact replica of your system, right? They only approximate some aspects of your system. And a digital twin, typically, with digital twins, you also try to update the model parameters in your digital twin online while interacting with the real system. Okay. You'll find lots of different definitions of what a digital twin is. Yes. Yeah, because it will have real-time, two-way interaction with the real process, right? So if you make changes to the process, you want to update your digital twin as well. Right. With the digital twin, that's right. Right. Exactly. That's yeah, exactly. Yeah. That's exactly why these digital twins are used. Right? People are very, especially in the industry, there's a lot of interest in building these digital twins so that they can play with the real plant offline and identify the best configurations, best solutions for the problems that they have before they go live. What time is the tea break? 11:30 is okay. Have you heard of interpretable machine learning or explainable machine learning? No? Okay. Neural networks or deep neural networks, they solve certain problems very effectively. But they don't tell you how they're solving those problems. In other words, when you use these black box machine learning tools, you lose intuition into your systems, into your process. You have absolutely no idea why or how they're functioning, right? And that is difficult to accept in certain industries. I'll give you an example. Does anyone here know model predictive controllers? I think somebody mentioned yesterday, model predictive controllers. So model predictive controller, it's not a PID controller, but it's a bit more complex. There is an optimization algorithm beneath it. You can apply it on large dimensional systems. For instance, you can have 10 inputs and 10 outputs. Model predictive controller would automatically operate and control the system with that many inputs, right? However, there are lots of industries where these model predictive controllers are used, but many times operators just shut this model predictive controller off because they don't fully understand what it's doing. I'll give you an example. This is an example from a refinery. We have a paper on this example. If you go to my website, you'll find it. So in this particular instance at this refinery, they had a very large model predictive controller that's running their processes. Everything was going smoothly, but at some point, the model predictive controller decided to drop the feed rate. This is in a refinery. So you basically get some crude, you refine it, and make the refined product. Right? So at some point, the model predictive controller decided to drop the feed rate. Okay. Dropping the feed rate sends alarms throughout the plant because when you drop the feed rate, you are making less of your product, which means you're not making meat. Perhaps there is a demand for the product. You've arbitrarily dropped your feed rate. Therefore, you're making less product. You'll make less money, right? So that's something that senior leaders don't like, right? So they wanted to know, why did you drop the feed rate, right? And the answer was, model predictive controller did that because we don't know what it's doing. It's trying to optimize something. We don't see any logical reason for it to drop the feed rate, is the response that the senior leaders got from the operators, right? So then their natural reaction was, okay, I'm going to take the model predictive controller offline. I'm going to drive the process myself, right? They were able to do that. Then they wanted to figure out, why is it that the model predictive controller dropped the feed rate? And it turned out that after some further analysis, their engineers found that a few days prior to that, they were doing some repairs on a certain line, and somebody put a clamp on a variable. A clamp on a variable means you put a constraint on the variable, and you say, okay, don't increase this variable. They changed that in the MPC code. They finished their repairs, and they forgot to remove that clamp in the model predictive controller. So it's an optimizer. It's just trying to find the optimal solution to whatever conditions it is facing, right? And that was not good. Right? So the point I'm trying to make here is, this happens quite often in the industry. When they don't understand how a certain algorithm is working, they tend to not use it or take it offline and run the plant on their own without these sophisticated algorithms. So being able to interpret what your algorithms are doing is extremely valuable when you sell these to the industries, to the users, especially in processes or industries where safety is a primary concern, right? If I don't understand what I'm using, I'm not likely to use it all the time because safety is a concern. So Liang Kao was a PhD student of mine. He's now a postdoc at MIT. He worked on this idea of interpretable machine learning. So he developed algorithms where the algorithms make these predictions, but they also tell you why they made that prediction. What is it that is causing a certain type of prediction? Another student of mine, I don't have his work on these slides, he designed a very interesting control algorithm, a reinforcement learning algorithm. His algorithm, the reinforcement learning agent, it controls the process, but it also prints out in text why it's taking certain actions. So he used a language model in conjunction with reinforcement learning. Now, the reinforcement learning, the traditional reinforcement learning algorithms, we don't know why it's doing what it's doing, right? So, I mean, we can mathematically explain, but that's not what we're looking for. We want to be able to, in very simple, intuitive, process-oriented language, explain why reinforcement learning is taking certain actions. So he was able to combine reinforcement learning with the language model and generate those explanations. So I would say that is explainable or interpretable machine learning. So you want to design your algorithms in such a way that they can be explained or interpreted. This is Gregory Lee. He worked on the health. He's still working on the health analytics project. So let me explain what this project is. You have patients coming to the emergency departments. Canada has a population of over 40 million, and I believe there are over 30 million visits to emergency departments every year. And the average time that patients spend in the emergency department is 7 to 8 hours. And often when patients are in the emergency department, nurses and doctors, they're just so overwhelmed with the volume of patients that they have to deal with. So in collaboration with a communications company and a couple of other colleagues in electrical engineering, we're doing a couple of things. One, we are developing sensors that the patients, while waiting, can wear. Those sensors will measure important variables like heart rate, oxygen saturation, blood pressure, etc. So live. So as soon as a patient comes in, we put these sensors on. Their measurements are then continuously monitored and sent into a cloud-based database. And once we have the data, we want to be able to triage these patients. So typically what happens is when you go to the emergency department, you wait there, and then a nurse will call you. They will measure all of those variables. Then they assess your condition and determine how serious it is. So that's called triaging. Right? So if you have 50 patients, then they rank them in terms of the seriousness of their illness so that the doctors can attend to the most serious, most ill patients. Right? So that's called triaging. And what Gregory did, was to build this algorithm, a triaging assistant algorithm, that takes these time series data and generates a text interpretation of the condition of a patient. Right now, these patients, when they come in, they go to the triage nurse. The nurse measures all of these variables. Based on that, he or she would describe the patient's condition. Right? They have high blood pressure or whatever, or low oxygen levels, etc. So they describe it, and then based on that description, they decide how to triage patients. What Gregory did was he, along with a nurse, Julie Lockington, Gregory and Julie, they had about 150,000 data points from different patients. They manually labeled 15,000 of those patients. Okay? So a label for this data, so for instance, heart rate, oxygen saturation, blood pressure, right? So you have to, in words, describe the condition of a patient based on those variables, which is right now done manually by nurses. Gregory and Julie, they manually labeled about 15,000 data points. 15,000 patients, or maybe multiple data points for the same patient. They labeled those, and then they built a small language model that automatically generates the text interpretation of the condition of a patient. Okay. So these are some risk levels. So bring in means it's very urgent. Consider bringing in. Watch carefully. Safe means, okay, the patient is not in any urgent need for attention. Right. Yeah, so this is another example where we use the language model. We are hoping to replace the work, some of the work at least, that the nurses are doing with this approach. All right. We are going to, in the next lecture, I'll start with data pre-processing and data visualization, etc. But I want to leave you with this final thought on artificial intelligence. And I think AI is poised to revolutionize how we live, learn, and solve global societal problems, whether they're related to curing diseases or combating climate change. And I think it's really your generation that's going to lead the way with AI, right? Okay, so I'm going to pause there. And did anyone check out the Aloha robots yesterday after the class? I can probably play one of those right now. I'll take questions. The robot at the top is from University of Toronto. They are trying to build these self-driving labs. This robot can do multiple experiments 24/7, nonstop, right? They're just working. I'll play one of these videos. That's just a photo of a train in Tokyo that Nathan took. Okay, so any questions?
Sir?
Yeah.
I have one question.
Yeah.
Sir, I want to ask that in reinforcement learning, like we perform codes and sometimes we have surrogate environment. But in real plant, reinforcement learning is there any future of reinforcement? I just want to know that reinforcement learning is just codes. We get control action based on codes. It solves an algorithm and we get the code, optimal action value. So like reinforcement learning doesn't, in some case, if there is a way that we can pre-train our agent and then we can deploy it, but in real plant we don't know that what kind of uncertainties we will be facing.
Right.
So is does this reinforcement learning has a future in industry, because uncertainties are always like we can't foresee uncertainties.
Right. You know, reinforcement learning works under uncertainty.
Even so it works. It's there in implementation, but every day we can't just. There is uncertainty in the environment, but reinforcement learning takes time to learn what can with episodes it learn.
Right.
So it it cannot provide action instantly. So like,
Right. There is, which is sort of similar to, what I mentioned earlier, right? So Honeywell tuner takes about 5 minutes to tune a controller. Reinforcement learning takes
15.
an hour to tune,
So
right?
sir, that's what I'm asking. These kinds of as a researcher we are working, but uncertainties in chemical plants are always
Right.
like unforeseen. In
Right.
case of robotics and car, we can do, because those kinds of uncertainties are very rare. Like we can foresee uncertainties in those kinds of situations. But in plants, like it would be very hazardous if we will fully dependent on reinforcement learning or model
Right.
predictive
Right.
control.
I mean, that's a good question, right?
So is there
What is-
so sir, in industries is there any people are using reinforcement learning?
I heard, I was at a conference in Toronto, and there was somebody from a company called AI Ops. In this, I think this guy was the chief marketing officer. He was saying that they have tried deep reinforcement learning in the industry, and it works better, right? I'm a little skeptical of his claims for a variety of reasons. Why would I want to use deep reinforcement learning when there are faster methods to use? Right? I think if we have to move towards, if you remember, very early on I mentioned that my goal is to build these self-driving industrial processes where just very few people can run an entire plant and not worry about it, right? People will argue that there are safety risks and so on and so forth. But let's say that's possible. That's our vision. That's where we want to go. Then you have to have controllers that are auto-tuning themselves, right, without any human involvement. If you look at traditional control algorithms, not the adaptive control algorithms, but the traditional control algorithms, they're not self-tuning. You tune them once and then you just sit back. If the performance drops, then you trigger auto-tuning. I think the advantage that reinforcement learning has is that you don't need to do that. You just turn it on and then you can sit back. It's always monitoring the performance, and if it needs changes, then it'll generate some data and retune the controller all by itself. Right? Now that's really where I want to go. I want to design controllers where I just turn them on once. I don't even bother building a model, nothing. I just take a controller, turn it on, and it just operates on its own. If I want to go there, reinforcement learning seems like a very appealing algorithm. But then we have to solve the problem of the algorithm being data hungry. We have to make sure that the algorithm is always going to be stable, right? Those are not fully solved problems in my mind.
So is it safe to depend on algorithms for industrial process fully dependent on AI?
Right. I mean,
Sir,
that's a great question, but that's,
So what do you think?
Yeah.
What is your in my opinion, fully dependent? It's
yeah.
very
I think, I mean, the risk is
dangerous.
always there, right? So for
Very
instance,
risky, huh?
yesterday, I think Elon Musk released robo-taxis. I don't know if you read that in the news. Um, you can make the same argument for cars on the road, self-driving cars, right? Is it safe to run them on the road? And Waymo had these cars for now 6 years, I think, 7 years, without any incidents. Yes, the way these algorithms are today, where the technology is, we probably don't want to install them and walk away from our industrial systems. It's going to be very risky, right? But if your goal is that, if your goal is to build these really autonomous industrial systems, we can work towards it, and maybe that is possible sometime in the future. And I think it is possible. We can add various safety constraints to whatever algorithms you develop, right? I think it's possible. Is the technology ready for that right now? No, I don't think so. But there are lots of tough research problems we have to tackle before we achieve a higher level of automation that requires minimal to no human intervention. It can take airplanes, right? They're such complex machines, and they're mostly automated. Humans are there to just monitor. Yeah, I can show this one video. So we have 5 minutes if you don't mind. Sorry about that noise. I think there's one video that I really like. I think it's this one. Let's see. All right. Okay. There are lots of videos there you can check them out. Okay, we'll see you in how much? How long is the break? 15. So we'll reconvene at 11:40.